Mm, um, we have this copies of the upper half plane. Okay, so here H is the upper half plane, and on this there is an action of SL2R to the power of n. Okay, and a component of SL2R acts on the corresponding component here. Okay, so if I have so this action is given by, so just let me say that if I have m equals to say m1 uh, mn, so these are matrices inside SL2R to the n, then how does it act? Then I have then m z. Oh, this is an m. Okay, so this is okay. Then for z equals yeah, so mz is defined by m1 z1 and so on up to mn, and then zn like this. So this is a very natural definition. Okay, then we also set out two notations. One was sz. Okay, so this is the first thing, recall. Okay, then the second one is that sz is equal to the sum of all the coordinates of z, and then nz is the product of all the coordinates like this. Okay, this is as a notation. Okay, I can take any complex numbers, whatever I want, and then I mean coordinates of so this z can be inside Cn, and then I can also write sz as well as nz. Okay, then we also I also wrote that if gamma is a subgroup of SL2R to the n, which is discrete, then it can be verified by showing that gamma x on x to the n discontinuously. Okay, that was one thing. And then for the definition of Hilbert modular forms, what we needed was we also needed the cusp. Okay, so cusp infinity. Okay, and then how was this defined? Okay, so just let me briefly recall. So for this I need the extended upper half plane here, copies of that. So for this I need this its bar, okay, to the n. Okay, and its bar has all real numbers as well as the point at infinity. Okay, wait, its bar equals to h union r bar, and r bar is the extended reals, r union infinity, like this. Okay, then what do I need to define the cusp at infinity? Well, we can talk about cusp only under an action of this of discrete subgroups of SL2R to the n. So let's take a discrete subgroup of SL to R to the n. So I have gamma to be a subgroup of SL2R to the n. And let's say that I have this gamma is discrete. Okay, then okay, so then you define the translations which are which are inside gamma. Okay, so then I put here, I look at this t bar of gamma, okay, which is the translations inside yeah, inside gamma. Okay, so the transformation. Okay, so any matrix which transforms. Okay, so transformation Z mapping to Z plus A. Okay, so these are going to be matrices which are upper triangular with 1 and 1 along the diagonal. Okay, so so this transformation is inside gamma. Okay, and these are the translations, and then we saw that this is a discrete subgroup of R to the N. Okay, so this is a discrete subgroup of R to the N, and then therefore this one is my T underline is going to be isomorphic to Z to the K, and we say that this T underline is a lattice if yeah, the number of generators of T underline is the same as N. Okay, then we had a system of multipliers to define the cusp. So this was one thing. The other one was multipliers, and then for that we needed okay, so and then the next one was I needed an epsilon which is inside R to the power of N. This is going to be a multiplier. Okay, so a multiplier of gamma of the discrete subgroup that I have. Okay, if there exists a B inside R to the N, okay, such that, okay, the transformation Z going to epsilon Z plus B is in gamma. Okay, so these are going to be matrices that look like, so epsilon B.
Sir, whether gamma is of finite index subgroup?
Gamma is a discrete subgroup of R to the power of N. In finite index subgroup of what?
No, of SL2R to the power N. It's gamma.
No, so you can think of gamma as like, let's say SL2Z.
Okay.
All right.
Yeah. No, my question is whether this gamma, which is a discrete subgroup of SL2R to the power N, whether this is of finite index subgroup. That is what, like in the case of classical modular form, we take this. I mean, gamma is of finite index subgroups. No, that is what congruent subgroups.
No. You are talking about SL2Z, not of SL2R.
Okay. Okay.
See, in your question, you should have said if gamma is a finite index subgroup of SL2Z
R to
to
the
the
power
N.
N.
Okay,
Oh.
not of
Okay.
R.
Okay.
Okay. Yeah. So here I'm not saying anything. We are just starting with any discrete subgroup. I mean, we are not saying what is the nature of gamma and so on. Okay.
Okay, sir.
Yeah. But those kinds of subgroups are going to be important for us. Okay.
Okay. Thank you, sir.
Yeah, so these are transformations that look like epsilon B01. Okay, I'm not writing this, but B has got many coordinates, n coordinates. Okay, epsilon also has n coordinates, and I just don't say that epsilon is inside to the n. Okay, we say that this epsilon is, so we don't take this, but we'd rather take epsilon to be, so maybe just let me include it here, epsilon to be totally positive. Yeah, so which means that if I write epsilon 1 up to epsilon n, right? Then each of these coordinates should be epsilon I is strictly bigger than 0. Okay, so in that case, we say that this epsilon is totally positive. And then I take the group of all these multipliers, okay, and then that we denoted by lambda. So lambda is the, so this is a group under multiplication, group of all the multipliers of gamma. Yeah, and then what we saw is that this is also a discrete subgroup of R plus to the power of n. So this is also a discrete subgroup of the positive reals, okay, under multiplication. So this is discrete, right? And then we had that, so this is discrete, and then it has a rank. So therefore this lambda will have a rank, and then we defined a cusp to be yeah. So just let me write it down for you here. So this was the definition. So definition. So so I have gamma to be a discrete subgroup of SL2 r to the power of n. So this has this is discrete. Okay. Then we say that gamma has a cusp. Okay, infinity. So this is nothing but I just write. Yeah. If the rank of this t bar, okay, so this is isomorphic to z to the n, and my lambda is isomorphic to z to the n minus 1, like this. So it should be free of rank n minus 1 lambda, and then okay, so yeah, and then so this is a cusp, and then we wanted to define other cusps, and then we did in gave the definition in the most natural way, which was that we said that yeah, so here was another definition. So so gamma, okay, has cusp kappa, okay, which is inside r to the n, okay, but I have to allow myself to include the point at infinity. So I take here this r bar, okay, then I can include the point at infinity. So if and only if, right? So for some, now A belong to SL2, then I don't leave, I don't stay inside gamma, okay? So if when I conjugate by some element of SL2R itself, SL2R and itself, okay, with A kappa equals to infinity, the group, this one, A gamma, A inverse, okay? So this has cusp at infinity. Okay, so it means that whenever I conjugate my gamma with an element of SL2R, then I get, I can call this, yeah, whatever I get here, kappa, okay, which will be A inverse of infinity to be a cusp. Okay, so so there could be infinitely many of these elements kappa. Okay, however, when we mod out by the action of gamma, when we look at equivalent cusps, okay, so there are going to be finitely many. All right, so that's the thing. I think one of you also asked this one, and then that comes from the the compactness of of x gamma. Okay, and then we also use this notation hn star denoted hn, okay, union the cusps of gamma, okay, all possible cusps of gamma, right? And then we said that if I look at this hn star, then it has a topology, which when if I restrict that topology to hn, then it gives me the usual topology, and then hn is open and dense subset of this hn star, and then like, yeah, so we know how to specify open neighborhoods of infinity. All right, now So this was one thing, and then we ended by saying, yeah. So where is this statement about? I mean, x comma. So let me just briefly look at it. Yeah. Okay. So and then we also said that I have this x gamma, which is it's an star, okay, with so the quotient under the action of gamma, and this has the quotient topology. All right, and then so we saw one proposition which says that this is a locally compact Hausdorff space. Okay, so this is locally compact Hausdorff, and then you can look at the neighborhood of infinity. Okay, union infinity here. This is a neighborhood of infinity. Okay, and there is an action of the stabilizer of gamma. Okay, I have to put the stabilizer of gamma because I want a subgroup that acts on this on UC union this point at infinity. Yeah, so gamma should leave that. I should be looking only at those elements of gamma which keeps this fixed gamma infinity. So I'm looking at gamma infinity. This is a stabilizer of infinity. Okay, and then there is an open embedding of this one to my x gamma, which is this hn star mod gamma. Okay, and this is an open embedding. Okay, open embedding. Okay, for sufficiently large C, and then this defines so elements, so subsets of this, which we see on the left hand side. Okay, so these are the defined basis for neighborhoods. Okay, so this defines a basis for neighborhoods of infinity. Okay, and then what? So there are, okay, so well, so we can look at, yeah, so as in the case of upper half plane modulo gamma, we can define things like fundamental domains and so on. Okay, and here in this case they are usually referred to as Siegel domains. Okay, and then yeah, so I don't know if I have the time to go through all those things, but just let me write this fact. Okay, so there are cusp sectors. Okay, so they are generalizations of you know fundamental sets in upper half plane model lattice here. Yeah, so what you do is that you have to take yeah, we have to be looking at parallelepipeds, okay, which are in the neighborhood of infinity. Okay, so I'm not going into the general definition of what the cusp sector is, but there are analogs of, or there are generalizations of the fundamental domains or fundamental sets which you see in upper half plane mod this lattice gamma. So maybe in the discussion I can give you a definition for this one. Okay, so so here is this so whatever we have discussed, we can summarize it by saying okay, so here is summary. Okay, so for gamma, discrete subgroup of SL2 r to the power of n. Okay, so this is discrete. X gamma is compact. Okay, and if we have so if I have, let's say, finitely many cusps, kappa 1, kappa 2, kappa h. So why finitely many? Okay, so so complete set of these are representatives. Okay, representatives of cusp classes. Then okay, so I have a fundamental set. Then we have, so this is like a fundamental domain. Okay, so fundamental set f equals to k union all this v1 union v2 union and so on, and how many of them? As many as there are cusps here. And then this k over here. Okay, so this is compact subset of h to the n. Okay, and then when you look at one vj, okay, so this will be a cusp sector at kappa j. Okay, so so this is a generalization of what you see in the case when you have upper half plane modulo gamma, okay, like SL2Z, that you have you know, you can write down your fundamental domain into a compact set. Yeah, the union, I mean these domains over here, v1 v2 is cusp sectors over here. Okay, so and why finitely many? Because I know that this is X gamma is compact. I can look at neighborhoods of all the cusp classes along with along with other open sets, and then they are going to cover this X gamma. And then since that's going to be that is going to be a cover, it will have a finite subcover, and hence there will be finitely many cusp sectors. Okay, and then therefore only finitely many cusp classes. All right, so that's the reason. This is the same as we have in the case of elliptic modular forms. Okay. Yeah. So just let me remark that. Okay. So let me remark that finite number of cusps follows from the compactness. A number of cusp classes. Okay, so these are not just cusp, but cusp classes. Compactness of X gamma. Okay, so we can also determine the local structure of the upper half plane modulo gamma. Yeah, but let's not go into that. So here is one thing which I want to point out, which is that yeah, so maybe I can leave it for later. Okay, so now so I have this, then I can start with the definition of, okay, so let's go back. let's go back and then let's look at how to get um, discrete subgroups of SL2R. So what are the things which we need? I need discrete subgroups, and I need inside the discrete subgroup, I need, okay, so we need, so this is this section maybe should be called Hilbert modular group. Okay, so what do I need? So we need a discrete subgroup of SL2R to the N. This. Okay, at the same time, I also need these translations. Okay, to define cusps, I need these translations to be free. Okay, abelian group of now this is SL2R with the N outside, the N outside here. And I need the multiplicative, the group of multipliers to be a discrete subgroup of rank N minus 1. Okay, all right. So there is one nice place where all this occurs. Okay, and there is a situation when I have a Hilbert modular group. Okay, so this is how I mean totally real fields come into the picture. Okay, so let me say this. So I have K, okay, to be a totally real number field. Okay, so in anticipation of the fact that I need lattices, okay, of rank n and lattices of rank n minus 1. Yeah, so if you recall the Dirichlet's unit theorem and so on, then you know that it's free, going to be free of this much rank. Okay. Um, so since I have that in mind, I mean since I know that I know that this is one situation where which will give me the discrete subgroups with all these properties. Okay, so that's why we look at totally real fields. So I have K to be a totally real number field, which means that this K over Q is a finite extension. So K over Q. So this is a finite extension. Yeah, and then so I will have embeddings. Okay, and K totally real means that I will have, so we then have, so as K is totally real, okay, so i.e. I'll have embeddings from K, okay, to C, okay, such that the images are all inside R, okay, such that the images, okay, let's say kj are inside R. So that's what it means to be totally real. Okay, so because K over Q is a finite extension, I will have embeddings. Yeah, so these are natural embeddings of K inside C, and then by totally real we mean that the image Kj, so they are all in R. Okay, and in fact we have in fact we have this is an isomorphism. Okay, so K is isomorphic as fields. Okay, this is inside R. Fine. Okay, so then what can I do? So I will have, since it's totally real, I will have n many embeddings. Okay, so if I call n to be the extension degree of k over q, then uh, we have n embeddings, okay, of k in C. Okay, so so let's call them as, so say that I have k inside kj, and then I have, if I pick an element a here, then it is mapped to, let's say, aj here. Okay, so here j is bigger than or equal to 1 and less than or equal to n. Okay, now what I can do is, so remember that this kj, each of them, yeah, so they're inside R. So that's the nice thing. So then I can think of k, okay, as an element of R to the power of n. Yeah, so then so this is the beautiful thing. So then we have the map from k to R to the power of n. Yeah, so what is this map? It's the obvious map. So if I take a here, then a is being mapped to a. Okay, so what is a1? A1 will be the image of a. Okay, and then under this embedding, okay, and then a to the n, like this. Okay, so often so from now on, when I say a to be an element of k, okay, we'll be identifying its image. Okay, whenever I write a will mean these things. Okay, so I'll give you an example now. So often, okay, we write a for the image itself, for the image itself. Okay, now what does this allow me? So now I have this map from, so this is an injective map. Okay, this is an injective map. Now what do I have then? So once I have this, then I can say that an element of GL2 of k. Okay, so this is mapped inside GL2 of R to the power of n. Okay, so verify this. So what I mean to say is that the map is given by M here, okay, and I'm going to write here M is A, B, C, D simply as elements of K. Then I need to associate M matrices for this one to this one, right? So M, the first matrix here, M, the second matrix here, and so on, M, the nth matrix here, like this. Yeah, where what is its MJ? Okay, so where MJ will be this matrix. Okay, A. So look at A here. So the jth, the image of the jth embedding, the of A, the image of the jth embedding of B, the image of the cth embedding of J, okay, and then of C, and then the image of the jth embedding of D here. So I'll give you an example now, okay, then everything will be clear. And then we are going to do this for J running from 1 to n. All right, now, so let me give you, I wrote down an example here, a nice one. Okay, so here is this example. Okay, so let me look at this example. So I have to look for a totally real fill. Okay, so one example. Okay, so I should take here k to be totally real fill. So yeah, so the easiest example is this one, k q square root of, say, some prime number p positive P prime. Yeah, then I have K over Q. Yeah, so this is of degree 2. Yeah, and then I'll have, so what are the embeddings? Okay, so let's look at the embeddings. Okay, so let's look at the embeddings of K. So K inside C. One embedding will be given by, so elements inside K look like, yeah, so it's going to look like X plus Y square root of P, right? So one embedding is going to be given by X plus Y root P being mapped to X plus Y root P. So this is the identity embedding. And then the next one will be defined by sending X plus Y root P to X minus Y root P, right? So this is like the conjugate embedding, okay? X plus Y root P being mapped to this one. So these are the two embeddings, okay, inside of K inside C, field embeddings. Then I'm going to say that, yeah, so then K is being mapped to here. I will have R2. Okay, so then K is being mapped to R2. If I take an element here, X plus Y root P, which is inside K, then it is going to be mapped to X plus Y root P, and then X minus Y root P, like this. Clear? So that's all I'm saying here. Yeah. Then if I take GL2 of K, yeah, then it will be mapped to GL2 of R2. Okay. So keep this in mind. So we'll be using this for our next examples. Then so one thing is that, so after this example, so we also identify GL2 of K, okay, with its image in GL2 of R, and like this. Okay, now here is this long-awaited definition. So what is this Hilbert modular group? Okay, so it's simply this object, so gamma K, which is equal to SL2 of OK. All right, OK is the ring of integers of K. So OK, so this is called the Hilbert modular group. Hilbert modular group. Okay. Here, okay. So this is the ring of integers of K. Yeah. So even though we wanted to have an analytic maps, okay, on the upper half plane, when I want to think of particular discrete subgroups, we are using number theory here. And so recall, so these are some number theoretic facts. So now, so you recall from your number theory that I have O, okay? So we write O for OK. So this is OK, and this is isomorphic to Z to the power of N as additive groups. Okay. All right. And so then then, and so then I have O. Okay, so this is discrete. This is discrete subgroup of R to the power of n. Okay, so this implies that SL2 of O. All right, so this is discrete subgroup of SL2 R to the n, like this. Yeah. Okay, so here is this remark. Yeah, so I have this SL2O. Now this is discrete. So therefore, by the first proposition which we saw, okay, what can I say from here regarding the action of SL2O, okay, which is my gamma k? What will be the gamma action on h to the n? Yeah, so we can conclude from here that gamma k acts on h to the n discontinuously. Yeah. So now what remains? So I have seen these examples. Now what remains? We have to determine, we should determine the cusps of gamma. Then we can talk about Hilbert modular forms. Um, so now, so the goal is to, yeah, so now the goal is the following, okay, to determine the cusps of gamma k. Gamma k is SL2 of OK. All right, so let's find out what the stabilizer of infinity is. Okay, so here, so you note that I have gamma infinity. So this will be all those elements inside gamma k. Gamma k is SL2O. Okay, so such that mz equals to epsilon square z plus a. Okay, where now I have a inside O, and then epsilon belonging to OK star. All right, so if I put here infinity, then yeah, this will be m of m applied to infinity will be infinity here. Okay, so these are all the stabilizers of infinity. So what does this mean? This means that, so therefore, so this means that what can I say about the translation module? So I can, yeah, so T of gamma k. So this will be the full group O. All right, and this is isomorphic to z to the power of n. Yeah, so the first condition for making infinity a cusp is satisfied. Now let's see if the other condition regarding the multiplier is also satisfied. And so this is the first thing. Yeah, and then for the second, I have to look at the group of multipliers. Okay, so here I have lambda to be equal to all those epsilon squared such that epsilon belongs to OK star. Yeah, this is because since the the multipliers are all totally positive, so I can write them as epsilon squared, and they have to be units, so they're inside OK star. All right, so since maybe right here, so since the multipliers are totally positive. Okay, so you can go and so look back what we recalled. So there also we mentioned that the multipliers are all totally positive. Yeah, so and then they are going to be inside OK star. Okay, so now what? So here comes this interesting fact, okay, which is called Dirichlet's unit theorem. Dirichlet's unit theorem. Okay, so what does it say? What does it say? It says that if I have OK star, sometimes I'm writing OK, sometimes I'm writing O, but okay, it's OK or yeah. So maybe I just write here O, and this is also O. All right. So this is isomorphic to z to the n minus 1 cross z mod 2z. Okay, this is a very elementary but very deep theorem. And then but what are so from here, what are the multipliers which are allowed? I'm allowed to take all those which are squares. Okay, so z mod 2 will give me plus minus 1. Okay, so I have to reject the minus 1 part. Yeah, so therefore I'll have here lambda to be isomorphic to z to the n minus 1. Yeah, so what is the upshot? Yeah, what can I say about whether infinity is a cusp or not? Well, I have all the conditions satisfied. Yeah, the translations are isomorphic to z to the power of n, and the multipliers are isomorphic to z to the n minus 1. So these were the two conditions, the two defining conditions for the infinity cusp. Okay, so therefore infinity is a cusp of gamma k. All right. Okay. Yeah. So now let me ask this question. Suppose I have a subgroup of gamma. Okay, subgroup of gamma. All right. And this is a finite index of finite index. Okay. Now, what can I say about the translations inside gamma naught? Yeah, so just they differ by a finite gamma naught is of finite index inside gamma. Okay, so try to think about this. So if gamma has a cusp at infinity, then gamma naught also has a cusp infinity. Okay, and conversely. Okay, and conversely. Okay, so I can produce many discrete subgroups. Once I have one, I can produce many other discrete subgroups where infinity is a cusp. Okay, so now what are some examples of normal subgroups of a finite index of gamma k? Okay, so these are some examples. So examples of normal subgroups of finite index of gamma k. Okay, so these are going to be some examples. And the first one, as somebody pointed out, yeah, I mean, we can talk about if there are principal congruent subgroups, then there are. So for that, we look at, so these are going to be the generalizations of the principal congruent subgroups. Okay, and what are these? So I take an ideal A, which is inside. Okay, so this is an ideal A inside O, and this is a non-zero ideal. Okay, then this I'm going to define principal congruent subgroup of level A. This A is an ideal. Okay, and how to define this? So this is, I mean, you know all these things, you have seen this. So gamma k of A, so this is defined by the kernel of the map from SL2 O to SL2 of O mod A. All right, now why is this is of finite index? Okay, it's easy to see that O mod A is finite. Yeah, so that's why I've taken here A to be non-zero. Okay, so here, here O, so this is number theoretic fact here, I mean, from algebraic number theory. So here O mod A is finite. Yeah, so SL2 of O mod A is finite, right? So therefore, this gamma k of A, so this will be subgroup of finite index. Yeah, so this implies gamma k of A. This is a subgroup of finite index, but okay, so we can also write this in the familiar form. Okay, so it consists of all those matrices inside gamma k such that M is congruent to E mod A here. Okay, E being yeah, identity matrix everywhere in all the components. Okay, so is normal because it is kernel, normal subgroup of finite index. Okay, and E is equal to identity. Yeah, 2 cross 2 identity matrix. So these are some of the congruent subgroups, and also there is one small exercise which one can do, is that note that I have gamma Ka is contained inside A gamma K A inverse. Okay, so when I write like this, it doesn't say anything, but if for some A not equal to 0, okay, whenever A belongs to GL2 of K. So whenever I have an A inside GL2 of K, I will have an ideal A. okay, such that gamma k of A is contained inside the conjugate of gamma k by A inverse. Okay, so this is kind of an elementary. You can see this for yourself. It's just an elementary calculation. So you just note that A is inside GL2K. Okay, so you look at the entries of A, and then you show that the denominators are going to be divisible by the denominators are going to divide out one natural number n L. Okay, so note, and then let's say there exists. So I'm just writing it because there is some number theory involved in doing this. So there exists L inside N such that both, okay, L times A and L times A inverse have integer coefficient, have integer entries. Okay, and then just you take A to be the ideal generated by L squared inside O. Okay, then this does the job because then I have A M A inverse minus E. So this will be equal to A times M minus E times A inverse. Yeah. So all of them are going to have entries in A, right? So this has entries in A, and we are done. So therefore, so this implies that A M A M A inverse. So this is congruent to E mod A. All right. So therefore, so this proves. Okay. So now, so just one more definition. We can do this in a special case, but so the question now is, what are the other cusps of gamma k? Okay, so this is a very interesting result. So here's what are the other cusps of gamma k? Okay, so cusps of gamma k equal to, we have found one, namely infinity. Okay, are there others? Okay, so that's the thing. Okay, so let me, so we are going to fill this out. So let's see what are the possibilities. Okay, so the first thing to observe is that let's take so maybe let's take a cusp of gamma. So let kappa be equal to, say, kappa 1. I'm writing it as kappa n. This is n. Okay, so this is inside R to the power of n. But as I said, when we're talking about cusps, we need to look at the extended reals here. Okay, so this be a cusp of gamma k. So maybe this is the first part here. Maybe call this as A. All right. Then what can I say about the stabilizer of kappa? Yeah. So this is by the definition, stabilizer of kappa. So this contains conjugate of a non-trivial translation. Yeah, of a non-trivial translation. Yeah, so i.e. it contains a matrix M, which is equal to A, B, C, D, okay, which is not equal to identity, okay, and A plus D equals to 2. Yeah, because that's what we are, those are the kinds of matrices which we get when we look at translations. Okay, so now then, yeah, so this M, even if I'm writing it as A, B, C, D, it consists of matrices MJ, right? So now, so what does this mean? This implies that, you know, the equation MJ, let's break it down into components, and then applied to kappa J equals to kappa J. Okay, so this has, yeah, you can see that this has a unique solution, only one solution. Okay, and if you write down all the solutions together, then you can compile them as kappa equals to D minus A divided by 2C, which belongs to K. Yeah, so I started with a kappa inside r bar to the power of n, which I'm calling it to be a cusp of gamma, and I ended up by showing that kappa is indeed an element of K. All right, so I can now go back and then fill out that the cusp of gamma is equal to infinity, which we have already shown, and then union K, the elements of K, of the field K. Okay, now if I can show that so this shows that the left hand side is contained in the right hand side. Now if I can go back and show that the right hand side is contained in the left hand side, then I can say that every K element of K is also a cusp of gamma. Okay, so let's do that. So now, so we pick an element of K, then look at this matrix A, which is equal to 0, 1, minus 1, A. Okay, this, the same A is here, huh? So this belongs to SL2 K. Yeah, and you map this text A to infinity. Okay, this takes A to infinity. Yeah, so you look at, so as A applied to A, okay, or A comma 1, A1, this is equal to 1 by minus A plus A, and this is infinity. All right, so this is the reason. So what does this mean? This implies that infinity is a cusp of A gamma K A inverse. All right, and this implies that A is a cusp of gamma K. Yeah, this is how we define the cusps of gamma K. All right, other than the infinity cusp. Okay, so now we have completed. We have successfully shown that the cusps of gamma consist of the cusp at infinity along with all the elements of the field K. All right. Okay. So now under the action of gamma K, it will so the number of equivalence classes, they are going to be much less. They are going to be just finitely many. Okay, and then let's see how many of these cusps, okay, are there when I take the gamma K action. Okay, so what are the cusp classes? Okay, so that's the next goal. Okay, so this is what are the cusp classes. Okay, so this is the next goal. And so for this, what I do is for each A inside K, all right, so we are going to look at an ideal. Okay, so look at the ideal. Generated by A and 1. So you look at this ideal. Okay, this is going to be the smallest ideal which contains both these two. Okay, and so i.e., so I have this map A. So given an element inside K, I'm going to look at so A1. This will be a fractional ideal. Okay, so and now so we can extend this to, so I send infinity to 1, the ideal generated by 1. This is going to be okay, the ring of integers. Okay, so then so we are saying that, so i.e., we get a map we have a map, okay, K union infinity to CL of K. Okay, so my C to CL of K. Yeah, so what is this? This is the set of ideal classes. Yeah, so this is the class group. This is the class group. The class group. Okay, so what is the map? So I'm sending A to the class of the ideal generated by A comma 1. This is going to be a fractional ideal if A belongs to K, and it's being sent to the ideal generated by 1, which is O, if A if A equals to infinity, infinity, like this. Okay. Now, so under this map, so we have this. So if I'm given any element of A, I have the class of a fractional ideal, and if I'm given any fractional ideal, then can I get an element of K? Okay, so that's the but so this map is whether this map is surjective or not. That's what I'm asking. Okay, so here's this lemma. So I want to check if the map, yeah. So if I can show that this map is surjective, and then the number of elements are the same under the action of gamma k, when we look at the gamma k equivalence classes, yeah, then the class group will turn out to be elements of the class group will turn out to be representatives of the cusp classes. That's the idea. Okay. So the map K union infinity to the class group of K. Okay, the first is that this map is surjective. Okay, and the second is that so fine, this map is surjective, but what about the cusp classes? Okay, and then we have this two cusps are equivalent. okay, with respect to the gamma k action, if and only if and only if corresponding ideal classes are equal. Okay, so this is elementary, but nice. So, well, so we first claim that if I have, let's pick an ideal inside the class group. Okay, so I have let A equals to, let's say, C1 D1. Yeah, so it's I mean, you would have seen this result from algebraic number theory, that if I pick any ideal, yeah, then as an ideal it always has two generators. Okay, so
Sir, I have a small question.
yes, please.
So this lemma essentially tells you that the class number is 1 if and only if there is exactly one equivalent class of cusps. Is that right?
Yes.
Okay.
Yeah.
Okay.
So if I take I think q square root of 5, does it have class number 1? I think so. Yeah, then essentially only infinity is the only cusp.
Okay.
Yeah. So if I pick any ideal A inside inside K, yeah, fractional ideal, then we can show, okay, as a consequence of Chinese embedding theorem, that it's generated by two elements. Okay, and then I want to check what happens if I have another set of generators, C2 D2. Okay, so this is an ideal inside K. Okay, so I'm just doing some elementary thing. Maybe we could have done this in the discussion, but it brings up some number theory, algebraic number theory thing. So then what am I claiming? Then there exists a matrix M which is inside SL2O, such that now I'm looking at C1D1 as a matrix. Okay, a row matrix times M is equal to C2 D2. Okay, so this calculation is going to be necessary. One can try to do this one. So the idea is that you take, okay, so the proof of the claim is as follows. Okay, so here, so for this take AJ BJ inside A inverse. Okay, J is equal to 1 comma 2, and then you look at this matrix MJ, which is equal to AJ BJ CJ DJ. Okay, with determinant 1 with determinant 1. I want elements inside SL2Z. Okay, so maybe I can put here such that. Yeah, and then you just look at, then you look at M, this matrix, M1 inverse M2. Then this will do the job. Okay, so then you can look at, then take this, and then you calculate, C1D1 M applied to M. Okay, and then this will turn out to be equal to 0, 1, and then M2, and then this is equal to your C2 D2. This finishes the proof of the claim. Okay. Now, for the proof of the other part, okay, about the equivalence, what we have to show is that if we start with two equivalent cusps, okay, now for this direction, so let kappa prime be equivalent cusps. Okay, then so if they're equivalent, I know that kappa prime is equal to, for some matrix M, okay, with M belonging to gamma k. Equivalent cusps under the action of gamma k. So we're looking at M belonging to gamma k, all right? Then this is just an elementary calculation. So then what can I say about this row vector kappa 1? So this is equal to kappa 1, yeah, by the transpose of M. And then this will look like something like, say, A kappa plus B, and then C kappa plus D, okay? And then this will be nothing but my kappa prime 1. Okay? So here MT is a transpose of M. Okay? So this finishes the fact, this proves the fact that if I have two equivalent cusps under the gamma k action, then they are equivalent under the under the action of this gamma k. And okay, so okay, so maybe I leave from this because it's a little bit it's kind of elementary. Okay, so from here we can complete the proof. Okay, so complete proof for this direction. Okay, now for the other direction, if I have two ideals, okay, such that if I have two cusps such that the corresponding ideals are equal, okay, so let kappa prime be cusps such that the corresponding ideals are equivalent, yeah, then what do I have? I have kappa 1, kappa comma 1 will be equal to, say, something like alpha applied to kappa 1 like this, right? Then I know that from the above claim, from the claim above, we can show that there exists an M. So then there exists an M belonging to SL2O such that kappa 1 equals to alpha kappa and then alpha, okay, times the transpose of some M, okay, and then this essentially shows that kappa prime is equal to M kappa. Okay, so I'm a bit sketchy, I'm sorry about this, but it trying to yeah, but the idea is that trying to even show that the that the equivalence the class of the what am I saying, the equivalence cusp classes that correspond to idle class groups, one has to do this rely on, one has to be yeah, one has to note this number theoretic facts. Okay, and then the last thing, so this is again, as we have seen this several times, okay, but just this is the theorem which I'm stating, for gamma k, So I have the space x gamma k. Now I'm writing x gamma k for x gamma, so which is defined by h n union k union infinity mod gamma k. So this is compact. Okay, this is compact. So this will be this is a result of whatever we have seen before. Yeah, so only I'm changing, I'm taking gamma k instead of gamma, and the number of classes here are going to be equal to the class number.